Okay, hello friends. Today we are going to start our last topic under the MCS Mechatronics and Control System, in which I am going to cover time domain analysis of control system. Till now, under the control system, we covered introduction of control systems, classification of control systems, mathematical modeling, transfer functions, and block diagram reduction methods. Now today I am studying the time domain analysis of control systems. Now most of the control systems use time as its independent variable. So it is important to analyze the response given by the system for the applied excitation, which is a function of time. Now analysis of response means what? To see the variation of output with respect to time. That is the meaning of analysis of response. The complete base of stability analysis that we are going to learn in detail in future, what is stability analysis, that is totally lies in the time response analysis. The system stability, system accuracy, and the complete evolution is always based on the time response analysis and corresponding result. That is the meaning of that is a requirement of time domain analysis. Now let's see the definition and classification of time response. What is the meaning of time response and what are the classification? Time response of control system means how output behave with respect to time. In short, very simple, how output changing with respect to time, that is a time response. It also defined as the response given by the system, which is a function of time, to applied excitation is called as a time response of a control system. How the parameter of the system is changing with respect to time, the output parameter is called as a, in short, time response analysis. In any practical system, output of a system takes some finite time to reach its final value. This time varies from the system to system and it depends on different factors. Similarly, final value achieved by the output is also depends upon different factors like friction, mass, or inertia of moving element, some non-linearities, etc. Now let's take the example. If suppose I am measuring some voltage or current with the help of ammeter. We are measuring the current with the help of ammeter. Then what will happen? While we are connecting that cord of that digital multimeter, analog multimeter to particular terminal to measure the current, that time initially the pointer of that analog multimeter will start rotating and try to achieving the required current. For example, I want to measure the suppose 2 ampere current. Thus the final state achieved by the output is called steady state, while the output variation within the time it takes to achieve the steady state is called as a transient response. As I said, initially the system will be transient state when it is changing from 0 to 2 ampere or 5 ampere, and when we achieve the 5 ampere, that time we can say we achieve the steady state. Now transient response, the output variation during the time it takes to achieve its final value is called as a transient state. Initially, as I said, in the ammeter, when we are connecting the cord to the particular terminal to measure the current, that time initially when the pointer of that analog multimeter is moving from 0 to, suppose I am measuring the 5 ampere, that time when it is traveling from 0 to 5 ampere, the system, that time is a transient response. The time required to achieve the final value is called as a transient period and it is denoted by Ct bracket T. If it is any system transient response die out after some time is called as a stable system. Mathematically, the stable operating system lies on limit T approaching infinity, Ct is equal to 0. Now what kind of output we are getting from the transient response? When the system has started showing its response to the applied excitation, when the system starts showing its response to the applied excitation, what is the rate of rise of output? From this parameter of the system can be designed which can withstand such rate of rise. It is also given indication about the speed of system, whether the output is increasing exponentially or oscillating. If output is oscillating, whether it's overshooting its final value, when it is settling down its final value. All this information matter much at the time of designing the system that we are getting from the transient response analysis. Now next we move towards the steady state response. It is a part of the time response which remain after completion of transient response vanishes from the system output. As I said, I am measuring the 5 ampere initially the pointer at 0. When we connect the cord to the particular terminal, the pointer start moving towards the 5 ampere. That time is transient response, and when after a certain amount of time pointer stop, that time we can say transient response vanish and we are getting the steady state. It can also be defined as a response of the system as time approaches infinite from the time at which transient responses completely dies out. The steady state response indicate the accuracy of the system. Symbolic steady state output represented by CSS. Now what kind of output we are getting? How much away the system output is from its desired value, that what kind of error is there, indicate the error. Whether this error is constant or varying with the time. So the entire information about the system performance can be obtained from the transient and steady state response analysis. Hence the total time response, the CD we can write as CT is equal to CSS, steady state response time, plus CD, transient response time. Now let's move towards the error. Now we got the steady state analysis. There are the two types of error, transient and steady state. Now we move towards the steady state error. The difference between desired output and actual output of the system is called as a steady state error, which is denoted by ESS, small ESS. As we know, steady state analysis, we are getting the error, and that error is called as a steady state error. This error indicated by the accuracy and play an important role in designing the particular system. For example, in this is a exponential system. Suppose some system is behaving exponential or some system behaving oscillating type of behavior with respect to time, how the system is changing. That time after this transient response, we are getting the steady state. That time this is our suppose desired value, and this is the we are achieving. Whatever the difference in that is a steady state error. And same way here, oscillating might be overshooting we are getting, and after a certain amount of time the magnitude of overshooting goes on decreasing, and after a certain amount of time we are getting a constant value, that is steady state. And again the difference between the desired and steady state error is called as the steady state error. Then this is example of exponential output, and this is example of oscillating output. Now standard test input, that is the most important part. In practically many signals are available which are the function of time, can be used as a reference input for the various control system. These signals are step, ramp, sawtooth type, square wave, triangle, etc. But while analyzing the system, it is highly impossible to consider each one of it as an input and steady state response. Because of that, here we are using some standard input for the testing purpose. Then first we are starting with the step input. It is a sudden application of an input at the specific time as shown in figure 7.2. A certain value magnitude, constant magnitude, we are applying the input. Mathematically we can write the input is nothing but R is nothing but input. RT is a function of time, is constant A if time is greater than or equal to 0. If time is less than 0, that time input is 0. For example, in this graph we can come to that it is a time. When time is 0, the input is 0, but when time is greater than 0, I am getting a constant value A. If the A is 1, that time is a unit step function denoted by U, small u bracket t. The Laplace of standard step input is A by S. Next standard input is RAM input. It is a constant rate of change in input, that is gradually application of input as shown in figure. Magnitude of RAM input is nothing but its slope mathematically is defined as we see here. When time is 0, that time input is 0, but as time increases, the magnitude of input is increasing, goes on decreasing. Because of that, here we can write down RT is equal to A into T. It is a multiplication of time. As time increases, the magnitude of A goes on increases. If time is greater than 0, if time is less than 0, equal to 0, that time we are getting input as 0. If A is 1, it is called a unit ramp input, and the Laplace of this function A by square. This is impossible, just note it down. We are using this Laplace in some derivation. Then step input Laplace is A by S, and ramp input Laplace is A by S square. Next is a parabolic input. This is input is 1 degree faster than the ramp input, in which the mathematically you can write here we are getting some kind of parabolic curve. Previously we are getting some kind of linear curve. Here we are getting parabolic curve in which the input is A by 2 t square when time is greater than 0, and when time is less than 0 equal to 0, that time input is 0. Where A is called as a magnitude of parabola. If A is 1, that is called a unique parabolic input, and the Laplace is A by S cube. And last one, the standard test input is impulse input. It is the input applied instantaneously for some short amount of time of very high amplitude as shown in figure 7.5. Very high input. It is a pulse whose magnitude is infinite while the width tends to 0, that is t approaching 0. Applied momentary area of impulse is nothing but its magnitude. If it is area's unit is called as a unit impulse input. Then we can write down when t is 0, that time magnitude is A, but t when it is non-zero, that time input is 0. These are the 4 standard inputs. Now in next video lecture we are going to cover the steady state analysis, and after following transient analysis. We will see you in the next lecture. Thank you very much. Bye bye. Take care.